So we've been looking at interacting objects problems, and we want to look at our Atwood's machine, our modified one, so an object is on a horizontal. But this time, we are going to include friction. We just make a little block a little bigger. There we go. Okay. In this particular case, we are going to have a kinetic friction with coefficient mu k. So the kinetic friction coefficient between the mass little m and this table surface is mu k times the normal force. And then there's no friction on mass big M because it's just hanging out. So just to clarify, the friction here is specifically between the mass little m and the table. We are still using the ideal rope and pulley approximation, so there's no friction here. Although I think after this problem, you can maybe start to see how we would incorporate that. Well, we know that we still have the same acceleration constraints. And so the acceleration of little m in the x direction, we're just going to call a. And the acceleration of big M in the y direction, we're going to call negative a. So we're going back to our standard coordinate system for right now. At the very end of the video, I will do it the other way as well. Yeah, so there we go. And so we're going to do our free body diagrams. Part of our free body diagrams are going to look very similar. But obviously there's going to be one more component, or aspect, I should say. Okay, so I forget how many marks I made everything last time. It's fine. So I'm going to make the weight of little m and the normal force on little m, both 3 marks. And we're going to have the tension pointing to the right. I'll just make it 4 marks. And we're going to have some friction pointing to the left. Now, it is not completely obvious from the statement of the problem whether the kinetic friction is going to be greater, less than, or equal to the tension. In part because I haven't actually asked officially the question, find the acceleration magnitude, just like we've been doing. But let's just assume for the moment, the math will tell us if this assumption is wrong. Let's assume for the moment that mass big M is going to speed up as it falls, therefore little m is going to speed up to the right, and therefore the net force needs to be to the right. We are going to have our force on big M. We know that the tension upward has to be the same number of boxes, just like we had here. So that'll be our T2. And our weight needs to be bigger than that in order for this to fall. So this will be W, which I will call that, go ahead and call that big mg. Okay. So our equations are pretty similar to what we had before. So the sum of forces in the y direction for big M, a big My, we have tension 2 pointing up, we have mg pointing down, and this is equal to minus ma. In the x direction over here, we have the sum of the forces in the x direction is equal to little m ax, and so we have tension 1 pointing to the right, we have kinetic friction pointing to the left, and that's going to be equal to ma. So, just like before, I didn't write out the sections this time, but we have the 2 tensions that are the same, and that slightly makes things a bit better. But if we look at our knowns and unknowns, well, we don't know tension, we don't know acceleration, but we don't immediately know the friction either. And so we need to look in the vertical direction here. And in this case, not always, But in this case, the normal force is equal to the weight of little m. And we know that the kinetic friction force has an equation of Fk equals mu kn. This is our coefficient that depends on the two materials. This is the normal force that tells us how smushed together the object little m and the surface are. And so this is going to be equal to mu k mg in this case. And we can plug that in up there. And so we get T minus mu k mg is equal to ma. And then we have T minus big mg is equal to negative big M A. Similar to before, we're going to solve for this by subtracting. You can always substitute, right? But I subtract, I eliminate. And so when we add these equations together, we get a big mg minus a mu k little mg is equal to little m plus big M A. And then we solve for a by dividing. And so we get, we still have a g hanging out. We have big M minus mu k little m and divided by little m plus big M. Okay. So this is the answer to the question, but let's do it the other way real quick. So I'm going to grab a picture of our setup here, and I'm going to copy. I'm going to come down here, I'm going to paste, and then I'm going to erase this coordinate system. And we're going to put back the crazy coordinate system we had in the last video, which is that the y is going to go to the right over here, and then curve around the pulley and go downward over here. And we're going to look at the external forces are equal to mass total times the acceleration of the system. Well, what are the external forces? On big M, we only have its weight. On little m, tension is not an external force, so we have the friction. And we still have the normal force and the weight of little m. They do cancel each other out, but if we don't at least think about them, we won't be able to calculate the friction. So if we look at our external forces, we have our capital Mg, it's in the positive y direction, Mg. We've got our little fk, which is in the negative y direction, right? The positive y up here is pointing to the right. So that is minus fk. And so we have little m plus big M times acceleration of our system, we're just calling A. Now is the one thing that we need to refer to the forces just on little m individually, because we need to figure out the magnitude of fk. We did already do that work up here. And so big M little g minus mu k little mg is equal to the total mass times A. And there we go. We divide it, we're done. We did it. Go us.